Welcome to Experimental Hall C at Jefferson Lab. Hall C is 150 feet in diameter and 60 feet tall. It was the first experimental hall to begin taking data at Jefferson Lab in 1995. During experiments conducted in Hall C, electron beams from CBAF enter the hall through an elevated pipe and are directed into an experimental target. A target might be any gas, liquid, or solid, which could also be polarized or cryogenically cooled. Inside the target, electrons collide with individual nuclei and the subatomic particles inside them. Two high-momentum spectrometers, or detector systems, capture and measure the particles that emerge from these collisions. Experiments conducted in Hall C typically focus on studies of the properties of the subatomic particles that build our visible universe, including atomic nuclei, protons, neutrons, and quarks.
Good afternoon, everyone, and welcome to Jefferson Lab's Bite-Size Science. This is the virtual lunchtime series of topics for the public. This is the fourth event in the series. We cover topics ranging from nuclear physics to accelerators, accelerator technology, and artificial intelligence and machine learning, all topics which are really important to the science we do here at Jefferson Lab. So these presentations are specifically tailored for you as the public, and anyone can submit a question into the chat, and I'll try to address your questions after this presentation. So we want to know how we can describe our universe. So as we walk outside at night, we look up and we see a sky, if it's clear, full of stars. And if we're lucky, we might even see planets. So the really incredible thing is that all of the matter that we see, all the visible stuff of the universe, is made up of things created right at the moment of the Big Bang. So the building blocks of matter that make up everything from the water we drink to the oceans we swim in to our physical bodies and even to the stuff made of stars basically can be understood in terms of a very fundamental way. So all of these things were created at the Big Bang. And so while you might think of someone like an astrophysicist or someone looking into a telescope to look outward to study the nature of the universe, we can also understand the fundamental building blocks of matter just by looking deeper into ourselves. And that's pretty much what we do here at Jefferson Lab, although not with a magnifying glass, but we can look at the building blocks of matter. We can look into protons and see quarks and attempt to describe the universe that we live in. So we look at the innermost workings of the nucleus of the atom to discover the secrets of matter. And studying the proton and the stuff that composes the proton, which are known as quarks, tells us about matter and the substance, which basically builds up then and accounts for properties at even like a very macro scale. So you talk about something big like the sun, or even going bigger into our visible universe. So protons were created right after the Big Bang and compose everything that we see that build the elements. So fundamental science in and of itself, we try to answer questions about what are the building blocks of matter, but it has benefits for everyone. So of course, when you go and start to try to better understand the proton, we've also been able to discover better ways to do cancer therapy, for example, where you can use protons to destroy cancerous tumors and preserve the tissue that you want to keep around that. So matter is the stuff that constitutes our observable universe. It builds you, me, the places we work, the places we live, the things we eat, and even the stars in the sky. So let's begin with something pretty simple piece of matter is the apples, the lunchtime series, right? So this is kind of what we're used to interacting with. And if we go to the next smaller scale, we can look at a molecule, for example. You are probably used to water, which is made up of a molecule of H2O. And molecules then are composed of atoms. So atoms are really, really small. And of course, Greek philosophers, when they first thought about this, thought that this was the most indivisible, this was an indivisible object. And so atoms are made up of both the nucleus and the electrons. And so the nucleus itself is made up of protons and neutrons. And so the protons that make up the nucleus, which make up the atom, basically tell you about the element that you're looking at. And so the scales that we're working at here are really, really, really small. So if you think of the atom, you have, about 1 billion atoms could line up across the top of your pinky finger. If you took the atom itself and made it the size of, say, a football field or a soccer field, then the nucleus of that atom, so the center part, would be about the width of your pinky nail, so pretty small. And so, as I mentioned, the elements, so the things that we sort of observe in our universe and experience, are defined by the number of protons that we have in the nucleus. So you have the periodic table, which you may remember, and so this is kind of arranged by number. So for an example shown here is a carbon nucleus, and which is has the number 6 attached to it. And so that's basically there to tell you that there's 6 protons in a carbon nucleus. You can vary the number of neutrons, but it's the number of protons that determines the element that we're looking at. And so while the proton may be the building block for the elemental type of description of the nucleus, the proton itself is composed of even tinier objects called quarks. And the quarks interact with each other through the strong force interaction, which is mediated by gluons. And so while we've known about quarks for some time, and the picture of the nucleus is really interesting because this is still not quite the full description. We know that if we could look even deeper, it gets a lot more complicated than that because there's so much energy stored inside of these quarks and gluons and their interactions. But let's take a step back for a moment, and we're just going to talk about the proton. So the proton is really special because it's the most stable particle that we know of that's composed of other particles. And so apart from the proton, everything else that we know of decays. So it has a very stable lifetime, long lifetime, much longer than the age of the universe that we know of, and that's very good for us. So additionally, we describe the proton, the type of particle, as a baryon, which means that it's made up of 3 quarks that you see kind of in this artistic rendering shown here. And so the proton also has mass. So the mass is really teeny, teeny, tiny, but it's the mass of this proton that actually makes up the mass of bigger objects that we see, whether you're talking about yourself when you step on your bathroom scale, or whether you talk about, how our planets move, for example. And so it's also characterized as having a positive charge. So when we study the proton, we want to understand basically how we can go from this description of the quarks and gluons inside the proton to describe what we know about the proton. And so that's really the big challenge. It sounds simple that we just know what's inside, but really it's quite challenging to go from the small to the bigger picture. I should also mention here that the other interesting thing as well about quarks is that there's no really free quarks. Quarks are always confined to be inside of another particle, and so in this case you have 3 quarks inside of the proton. So the fact that the proton is stable and you have these 3 quarks that you can't observe by themselves makes it a really great way to study the building blocks of matter. So protons have mass. When we stand on a bathroom scale and we weigh ourselves, trying to understand our weight, which is related to our mass, which is also related to the number of protons in our body. So the craziest thing is that if we could take the proton and put that on a scale and measure its mass, and then if you could take the mass of the 3 quarks that make up the proton, you would find that these 3 quarks only account for about 1% of the mass of the proton. So I've also told you that there's gluons inside of the proton, but those have no mass. So where's all the mass coming from? Turns out that Einstein gave us a clue. He taught us that there exists a relationship between the energy of an object, as determined by its resting mass, so this E equals mc squared, proportional to speed of light squared. And we know that these quarks inside of the nucleus, these are the 3 primary ones that I mentioned, they're moving around, they're relativistic particles. They're zipping around and doing all sorts of activities inside the proton. And so while I told you that the gluons themselves are massless, the rest mass of the proton then has to be composed of both the mass of the resting mass of these quarks, as well as the activity of the moving quarks and gluons inside the proton. So much is happening, actually, that it's this energy that actually accounts for 99% of the proton's mass. So all the energy stored up inside of this proton can also produce other objects, these quark-antiquark pairs, which we call kind of this sea of quarks that we see, which pop in and out of existence. So protons are characterized, of course, I told you, as having a positive charge. And so we know that the charge basically comes from these three quarks, where you have, not very creatively named, but you have two up quarks and a down quark, for example, and they have fractional charges. So when you add all of these charges, you get a positive one charge, which is the exact opposite, but same magnitude as the electron charge. And so that's very interesting because it's the fact that these three quarks are confined to the proton, they sort of can generate what we kind of call the proton charge radius, right? So we have this confined region that these quarks live in, and we can actually have then a measurable radius that they live. And so this was a kind of an artistic rendering that you see here on the right from a recent experiment at Jefferson Lab, where we measured the proton charge radius and measured it very high precision using electrons scattering off of the proton. So the wild part about all these things that we know about protons, that it's not as if we can sort of just take a microscope, zoom in with it, and look at it physically with our eyes. So imagine if you were given this pocket watch and a lab notebook, and I asked you to determine how it works. So you could probably study this for some time. You could observe how the minute hand, the longer hand goes around the face of the clock, every time that the shorter hand moves from number to number. You would also maybe notice that the shorter hand moves all the way around the clock 2 times before the next sun, with the next sun rising. And so you could make sort of observations about that they always move in the same direction. And you would have a pretty good description that you could even predict what it's going to do next. So you could develop a pretty good concept of how it works, but not without really fundamentally understanding the mechanisms behind it. And so if you were to take this watch and then drop it on the ground or interact with it somehow, you might be able to see that the inside is made up, of course, of gears. And so if you just have the gears and you just have your observations of the face of the watch, then the real challenge then is assembling these gears to make, really put it together to see and observe what it does and why. So that's sort of this dance that we kind of do, the story of nuclear physics, that we know something about the gears, and we study the watch face, but the precise connections and details are really still, it's a back and forth between theory and, of course, experiment to really build this cohesive picture of our understanding. So let me explain how we study the proton. So imagine standing before this very dark tunnel, and I tell you that there's a famous statue inside, and the only way you can figure out what it looks like is by throwing this baseball. So you could probably throw it down. You might lose it a few times before you hit this statue. But if you could, every time you throw it, calculate the angle at which you threw it and then how it bounced back to you, you might be able to eventually determine that you found Rodin's thinking man. And so you would have to repeat this experiment many, many times. And of course, to get the fine details around his face and his hands, you would probably need a smaller ball. But we do kind of something similar when we study the proton because we don't have a microscope, for example, to look at it with. So we replace the ball with an electron. And basically, in that case, then, our thinking man just became our quarks and gluons. And we can use these high-energy electron scatterings to understand the structure of the proton. So this is an aerial view of Jefferson Lab, located here in Newport News, Virginia. And so we can generate electron beams up to 12 GeV. They accelerate around the accelerator as shown here. And so we have 4 experimental halls, creatively named A, B, C, and D. But the idea here is that this beam can be split off to any or all of these halls at the same time, and they can interact with a different target, and they have different detectors inside of them that can measure the reaction that you're looking at. So As you saw just prior to the start of my presentation, you saw the video of Hall C. And so here's the cutaway picture that you see on the right of Hall C, where we're standing. The beam would be coming into the picture from behind, so you can see it's coming at you. And in the center is the kind of like a big tin can that contains our target, which could be hydrogen or carbon or something that's interesting to look at. And then our unscattered electrons would go off into the beam pipe that goes off to the right. But if we were to knock out, say, like an electron or a proton, then we would steer these using these big giant magnets that you see on the left and right sides up into detector stacks, measure them. So Jefferson Lab is really like a microscope. We can choose the energy and the momentum transfer to determine what it is that we want to study. We can look at the whole proton. We can scatter off just the quarks inside of the proton. And with enough fine-tuning, you can even access this C-quark distribution, which, of course, arises from the splitting of these gluons. So here's a picture showing the idea of proton knockout from a nucleus, as was recently performed in our Hall C experiment. Here you can think of sort of what we're doing is called elastic scattering. So you can think of like billiards, like playing pool, where a ball would come in and scatter. Okay. So in this particular experiment, we sent an electron beam in, as shown here. This is sort of an artistic rendering, onto the nucleus, this is a carbon nucleus, and we knocked a proton out. And you can measure things like, for example, what is the probability that this proton survives to exit the nucleus, that we can measure it. Or you could also study, for example, what we were looking for was protons where the quarks were in different types of configurations. We were looking for where the quarks were all kind of overlapping right on top of each other. The protons in the nucleus are a bit like people. If they're far apart from each other, then they may have no interaction. At medium distances, they can exchange particles where they're attractive. And at short distances, they're with their quark distributions that would then become overlapping and repel each other very strongly. And so these types of, so we can do these types of experiments similar to what I just mentioned where I was talking about proton knockout, and you can measure, you can try to recreate the picture of what the proton was doing before it knocked out the electron.
Again, let's see.
Hello? Okay, I think we're back on. We're trying to check if my microphone could be improved. So hopefully you can hear me now. So I'm going to talk about, so the other type of reaction we can do besides this proton knockout and looking at protons, for example, in the nucleus, is we can look at proton substructure. So one thing we can do is you can break up the proton, like kind of, this is really trying to understand the gears of our clock. Then we can break up the proton and see what comes out. So some of the interesting observations we've studied this way, this is directly scattering off of the quarks, is we can study the quark distributions in the nucleus, in the proton, and we can also study the gluonic contribution. So other things that we've observed, of course, is that the proton structure, this was sort of an inadvertent thing that we observed and that we're still trying to explain, is that the proton structure itself changes when you're inside of a nucleus, and then versus that of being a free proton. And so this is a pretty interesting effect, and the origin is still not clear. So to summarize, and I hope you've been able to hear, I know we've had some microphone difficulties, I just want to bring it back to the beginning and just mention that by studying the proton, we learn about the strong force, which tells us about the nuclear force that binds the nucleus and of the atom and composes all of the known matter that we see and experience. So we can gain insights into matter across the scales. Protons can tell us about the Big Bang and the origins of the universe. And importantly, protons are sort of a fundamental part of our life, even if we're only ever thinking about them on a bathroom scale. So the research of the protons pushes us to, improve technologies and improve, all sorts of imaging and how we think about things. And we can even learn about things that can help us in our everyday life, even to include improving cancer therapy. So the other thing I'd like to just mention before finishing this is that at Jefferson Lab, the 12 GeV beam energy that we have a very exciting program in all 4 halls that study different aspects of the proton. And so of course, the goal would be that we can combine all of these different pictures that we have of the proton and explain things from quarks and gluons to the proton to the nucleus and really build a cohesive framework of our understanding. So this concludes the presentation part, and I look forward to answering your questions. So I will turn it over to Rebecca.
All right, Holly, thanks so much for all of that great information about the proton. Again, we apologize for some of the sound issues. There will be an alternate recording, so everyone can go back and listen again to learn about all this great info. As Holly mentioned, I'll be helping to moderate some of the questions. We have a few questions that were sent to us ahead of your presentation, so we'll go ahead and kick off the conversation with those. And as a reminder, please feel free to ask Holly any questions about the proton in the chat. So the first question that was submitted to us is, why is it important to study the proton?
So the proton, as I mentioned, is really special because it's made up of quarks and gluons, but it's the most stable particle that we know of. To date, we don't know that it decays. And so that makes it really the best place to study the building blocks of matter, the quarks and gluons. And so, of course, if we need like a good laboratory to look at that, then the proton's really the place to look. And, in addition to that, it kind of gives us insights into what the universe was like. You can even trace it back into like what the universe was like at the Big Bang. We know that right at the Big Bang, there was apparently free quarks. Then they all combined to make the matter that built everything we see today. And so, we don't know why there's no more free quarks, but the proton is really the place that we can study them. And so I would also just like to mention that, it's interesting to study because we also never know quite what you're going to find, and that can improve technology and, for example, improves cancer therapy type research. So it's good for all sorts of things.
Okay, awesome, thank you. how do you explain particles popping in and out of existence? That is a question from the chat.
Yeah, so this is kind of what we describe as like virtual particles. So you would have like these gluons, these gluonic fields can split, generating quark-antiquark pairs. And then they sort of kind of annihilate with each other. So they pop up and then they go away. And so this is all the things happening inside of the nucleus of the, inside of the proton itself.
Okay, awesome. We have another question in the chat. Do you think to collide protons in the JLab Accelerator to study, let me reword this a little bit. Can we collide protons in the accelerator to study dark matter?
So that's an interesting question. So we don't accelerate protons at Jefferson Lab, but other places do. And so it just requires much bigger machine. You know, it's a much more massive object than the electron, which is and the electron. So the electron, I always argue, is like the nice thing to look at anything else because it's point-like. It's not made up of anything else. When you start colliding protons, it gets much more complicated because you can imagine that when it collides into something, it's sort of like if you had a pancake with blueberries in it and you wanted to look at, you know, what's happening when the blueberries react. And so it's much more complicated. But you can study dark matter or look for it at any rate in either type of cases. We have programs here at Jefferson Lab that look at dark matter using the electron beam. So if there's a heavy photon search experiment. There's also a beam dump experiment and all of these things. So there's theories that predict that you could see these types of effects where you would have, like you have an ordinary standard model photon, you could have sort of a dark matter component like that, like a dark photon, and you could radiate it from accelerating electrons on heavy targets. So that is something that we look at the lab.
Okay, another question in the chat is, what is your favorite open problem related to the structure of the proton?
So I guess maybe I'm a big picture kind of person, but I want to know how, so it's the strong interaction is what happens in between the quarks and the gluons, right? It's the gluons mediate the strong interaction. And so this binds, you know, this is what creates the proton, sort of, these things are bound together. And then, but then, you know, on a bigger scale, you're looking at protons and neutrons, and they're doing this sort of dance inside of the nucleus. And so we want to know what holds the nucleus together. But the interactions between the protons and the neutrons inside of the nucleus is far less than what's happening inside of the proton, and it comes from that. It's sort of like a leakage effect from these quark-gluon interactions inside of the proton. So to me, I would like to understand the connection between these two pictures, because it's not always, it's still not completely understood, and it's really interesting because it's inside of all of us and inside of matter. So.
Okay, it looks like we have time for one more question, and we'll go with a question that was pre-submitted to us. Okay. Do you believe we'll ever see a proton in our lifetime?
Okay, fun question. So I guess the question here, of course, is asking how do you see the proton? So I had, you know, beautiful pictures in my talks that I found of what we think protons could look like, but the truth is in order to see something, you have to have photons bouncing off of an object at a frequency of visible light that can be, that your eyes are, which are like these wonderful photon detectors for certain visible wavelength frequencies of light. And so, unfortunately, the proton is far too small to reflect the kind of light that would bounce off of the proton. So even if you could magnify it enough, right, that would be, you would never be able to actually see it using light in that way. But we can use other means and that's basically what we do here at Jefferson Lab. So we use other means of the scale to observe the proton. Additionally, of course, you have the Heisenberg uncertainty principle. So even if you could hone in far enough on the position of this proton to observe it, it would have very high momentum. So this wouldn't be so easy. So it's not, I guess it's not a technology question. It's a question of how to image it. And so it's not necessarily something we would image in visible light frequency.
Okay, thank you for that thorough explanation. That's all we have time for today, so I'm going to go ahead and kick it back to you.
Okay, thank you, Rebecca. So with that, I just want to thank you for listening to this presentation. Thank you for joining us for this Bite-Size Science talk. And I hope that you will join us again on August 12th for the next talk, which will be exploring the world of quarks and gluons with Nobuo Sato. So thank you for joining.